Lesson 11, Improper Integrals. In our unit on integration, we discovered that a definite integral was defined as a limit of a Riemann sum. We use the fundamental theorem of calculus to evaluate definite integrals. Now we want to explore some integrals that do not meet the conditions of what we call a proper integral. So the definition of a proper integral, an integral expression of the form the integral from a to b f of x dx is considered a proper integral if the limits and function are bounded. Proper integrals are always well defined. That means the limit converges. That is, the function is defined and bounded on the interval ab. The limits of integration are finite. They do not go to infinity or negative infinity, and the function has only finitely many discontinuities in the interval. So in this lesson, we investigate what happens when these conditions are not met. Integrals are considered improper if one of two things occur when defining the definite integral, the integral from a to b f of x dx on the closed interval ab. Either a or b is infinity, okay, so one of your limits of integration could be infinity or negative infinity. Type 2, the region defined by f of x has an infinite discontinuity in the closed interval AB. So we will show you these two different types. So example number 1, sketch the infinite region R that lies under the curve y equals 1 over x squared above the x-axis. And of course, you know, if I put a 1 in, I'm going to get a 1 because I get 1 over 1 squared. And if I put a 2 in, I'm going to get 1/4. So you can see how this quickly goes to hover right above the x-axis. If I put a 1/2 in, I get 4. So if I was, you know, doing like, if I had 2, 3, 4, if I put a 1/2 in, I'd be going up to that point already. That was my point 1/2 comma 4. This was my point 2 comma 1/4, along with my point 1, 1. So you can see that if I started here at 1 and I was trying to find the area under the curve from 1 to some t value, okay, that was, you know, that's what models this integral. So the area a of t is equivalent to the integral from 1 to t of 1 over x squared dx. And so if I was going to do this, I would say, well, I've got the integral from 1 to t, and I've got x to the negative 2 dx. So that's going to be x to the negative 2 plus 1 divided by negative 2 plus 1, and from 1 to t. Move this up here. So that's going to give me negative 1 over t minus negative 1 over 1. So negative 1 over t plus 1. Now imagine, I put the t right here in my graph, but imagine if it just kept going and t was, you know, down here, or t was, you know, who knows where. As your t gets larger, this whole thing right here goes to 0. And so this becomes 1. So you can imagine as your t gets larger here, I mean, your answer to your integral right now is negative 1 over t plus 1. But as t goes to infinity, your area is going to approach 1. So it says, what does the answer tell you about the value of a of t? And so I would say, well, that tells me that that area approaches 1, which seems weird because it's like, well, if, you know, t could just keep going, but it's so small, it's so close to the x-axis that it does actually add up to 1. So now if we found the limit as t approaches infinity of this a of t, that would be the limit as t approaches infinity of our negative 1 over t plus 1. And there you can also see that if you put infinity into this negative 1 over t, it's going to approach 0, and your limit is going to be 1. Okay? All right, so now, the definition of improper integrals type 1. Well, underneath type 1, you have a couple of different things. You have case 1 and 2, which is the improper integral converges if the limit exists. Otherwise, the improper integral diverges. And case 3, this improper integral requires both of the integrals to be convergent in order for the integral to also be convergent. If either of the two integrals is divergent, then so is this integral. Okay, so let's look at the 3 cases. Number 1, we have an integral going from a constant a to infinity, okay? And what we're going to end up doing is we're going to say, I'm going to put a letter in, and usually, since our knowledge of these integrals is from a to b, if my infinity is up here, I usually, let's say it was like, 5 to infinity or something like that. For this function, I would change that to, what you're going to do is say the limit as b approaches infinity, and then just put that b in. And the reason why we say b is because we're thinking of the integral from a to b, okay? But that is what you're going to do on these improper integrals. You cannot put infinity in. You have to change it to a limit. So that's the crux of this whole thing. So if f is continuous on the interval, the closed interval from a to infinity, then the integral from a to infinity, f of x dx, equals the limit as b approaches infinity of the integral from a to b, f of x dx. Now, the second case is, what if this is negative infinity? What if a is negative infinity, okay? And what if f is continuous on the interval negative infinity to b? So then I would say the limit as a goes to negative infinity, because I'm replacing my my lower limit of integration with that variable a, and then going to a number, and b is just some number, okay? But the thing is, you're changing it to a limit, and that's what you're going to be doing for all of these improper integrals. And here's our case 3. It's going from negative infinity to positive infinity. So we have 2 separate. And it looks like on the paper, which I just now noticed, oh, maybe not. Okay, they just changed it to, just pick a number. Usually I pick 0. I mean, unless, there's some problem with 0. But, if you've got a function that's continuous, from negative infinity to positive infinity, midway through is like 0. But you could choose any value c. C can be any real number. And you're just going to say, I'm going to take negative infinity to this real number, f of x dx, plus, and then take that number to infinity. And that together will give you that integral from negative infinity to infinity. Now, of course, these need to, be changed to limit problems, okay? Because they've got a negative infinity. The first one has a negative infinity. The second one has an infinity, okay? So now, helpful hints. Remember that evaluating an improper integral is really 2 problems. It is an integral problem and a limit problem. So we're going to, do the integral first, and then we'll do the limit. So you just got to remember, you got to do them separate, and usually the integral comes first. So when breaking down improper integrals, be sure each integral is improper at only one place. That one place should be either the lower limit of integration or the upper limit of integration, okay? So you do have to remember that. And as we go, I will, be reminding you guys, of everything, all of these things going on, okay? So let's look at example number 2. So for example number 2, we have, I'm just going to change my color. Okay, we have the integral from 1 to infinity of 1 over x dx, okay? So we're going to say, well, I know that I can't take it to infinity. So what I'm going to do is take the integral from 1 to b, 1 over x dx, but then I'm going to take my limit as b goes to infinity. So I'm going to work on this integral first, then I will take the limit, okay? But you still have to keep writing your limit. But it's going to be on the outside, and you don't have to worry about it right just yet. So I know that if I take the derivative of ln x, I get 1 over x. So therefore, my integral, my antiderivative is ln x. And so that gives me the limit as b goes to infinity. Now I'm going to use my fundamental theorem of calculus, ln b minus ln 1. Remember that ln 1 goes to 0. So this becomes the limit as b goes to infinity of ln b, because minus 0 we just don't worry about. And I did not have to worry about putting an absolute value sign on that, because I knew that I was going from 1 to infinity. All of those values were positive, so I didn't even worry about putting an absolute value sign on it, okay? So now we're going to look at our limit. We are talking about the natural log of infinity, basically, right? Because you're putting infinity in, you're doing substitution. Think about the natural log function, okay? I know what the natural log function looks like. This is what the natural log function looks like. What is happening as my x's get larger? Well, it's happening slowly, but my y values are slowly going to infinity, okay? So the natural log of infinity is infinity. If you get an answer of infinity, that means that it diverges, okay? That means that when you're taking, and by the way, I'm going to sketch a graph of the function 1 over x, and so when I put a 1 in, I get a 1. When I put a 2 in, I get a 1/2. And remember, it has a little bit more room in between the x-axis and the function than 1 over x squared. Because 1 over x squared at 2, it gave me 1/4, and it quickly gives you very, very, very small values because you're squaring it every time. So at x equals 3, this one is just 1/3, where the other one would have been 1/9. Okay, so, but you do have a similar looking figure, but it has a different answer, and we will be talking about that because this one, as I go to infinity here, this one diverges. That means that this area is infinite, where the one that was up here that we looked at, it got so small so fast right here, it actually summed up to 1. Okay, and the only thing that was a little bit different was that the first one was x squared, and the second one was just plain old x to the first power. I'm making a video, I'm so sorry. Oh yeah, absolutely.
Just need to get to the math office.
No
Sorry about
problem,
that,
that's
Laura.
okay, that's okay. But that's why I wasn't talking.
I figure you're a tutor or something, I just didn't want to interrupt, but...
Yes, no problem. Thank you. Anyway, sorry about that, guys. So this one, you know, the area, even though it's just one away, you know, one power away, it actually goes to infinity as x goes to infinity, where the other one just goes to 1. So I think that's pretty interesting, okay? All right, so now, theorem. The integral from 1 to infinity of 1 over x to the p. Now, this one is important that you realize, because the thing that we just talked about is very important. because 1 over x diverges. So when p is 1, it definitely diverges. And when p is 2, it converges. Even though I didn't show you that, since I got an exact answer here on example number 1, I got an actual finite answer, we can say that this converges because I got a finite answer. Where this one, I got an infinite answer, and so we said it diverged. So now our theorem, if we have the integral from 1 to infinity of 1 over x to the p, it is convergent when p is greater than 1. But it is divergent when p is between 0 and 1, but it can equal 1 and still be divergent, okay? Because we said that 1 over x to the 1 is divergent. And so let's go ahead and do another example. So this one, you can see negative infinity is on the lower limit of integration. So I'm just going to call it a. I'm going to let a approach that negative infinity, and then I'm going to put my a in right where that was. This one is perfect for tabular integration. So I've got my u and my dv, x1, 0, and dv is just e to the x every single time. And remember, this times this times this one gets multiplied also by positive 1. This one also then gets multiplied by negative 1. So let's go ahead and look at our limit as a goes to negative infinity. Thank you. So this becomes positive 1 times x times e to the x is x e to the x, and then negative 1 times e to the x, so minus e to the x, okay? And from a to 0. So we've got our limit as a goes to negative infinity. This is going to be 0 times e to the 0 minus e to the 0 minus a times e to the a minus e to the a. And of course, this turns to 0. But this one is negative 1, right? So be careful there. The limit as a goes to negative infinity. This is going to be negative 1 minus a times e to the a plus e to the a. And so now, if I put negative infinity into this,